Hello everyone, and welcome back to the AI Research Roundup. I'm your host Alex. Today is May 5th, 2025. We're looking at an interesting ICLR conference paper, published about 3.5 months ago, called Residual Deep Gaussian Processes on Manifolds. Okay, so this paper essentially proposes a new way to apply deep Gaussian processes, which are powerful statistical models, directly to data that lives on curved surfaces, or manifolds, not just flat Euclidean space. Alright, so let's look at how they actually build these layers. This figure gives a nice visual intuition. You start with points on the manifold, like this sphere. Then each layer applies a Gaussian vector field, or GVF, which models a displacement, and uses the manifold's exponential map to kind of push the points along that displacement. This creates the residual structure, layer by layer, ultimately leading to the final prediction. Okay, so building on that idea of Gaussian vector fields, this figure shows different ways you can actually construct those GVFs on the manifold, specifically illustrated here on a sphere. We see options like projected GVFs, coordinate frame GVFs, and Hodge GVFs. These different constructions essentially define the types of displacement patterns the model can learn at each layer. The Hodge GVF, shown in C, turns out to be particularly effective. Okay, so moving to the results. This figure shows how these different models perform on a synthetic regression task. We're looking at the negative log predictive density, or NLPD. Lower means better predictions. Alright, the key takeaway is that as we add more layers and use more data, performance improves. You can see the green line, representing that Hodge GVF approach with interdomain variables, generally performs best, especially for larger datasets. Beyond just regression, this figure looks at Bayesian optimization. Part A shows a complex, irregular function on the sphere, and Part B compares how well the deep model, shown in blue, versus a shallow model in orange, optimizes this function, and another one called Ackley. Okay, the deep model finds a better solution, lower regret, especially for the irregular function as the optimization progresses, showing its advantage for complex tasks. Alright, so moving beyond synthetic benchmarks and optimization, this figure demonstrates a real-world application, modeling wind velocity on Earth. Part A shows the ground truth wind vectors and the sparse training data locations from a satellite track. Then, Part B visualizes the model's performance, showing the difference between prediction and truth as arrows, and importantly, the predictive uncertainty as a color map. This highlights the model's ability to handle complex, real-world manifold data. Okay, building on the wind modeling application, this plot digs deeper into that performance. It shows the negative log predictive density, again, lower is better, versus the number of layers in the model. We see this for 3 different altitudes. Alright, adding layers, particularly going from 1 to 2 or 3, significantly improves the predictions, lowering the NLPD. This benefit is especially noticeable at the lowest altitude, 0.1 kilometers, suggesting the deep model excels with more complex wind patterns. So, wrapping things up, we've seen that these residual deep Gaussian processes offer a really powerful way to extend deep learning to curved spaces. Well, the key takeaway is that this layered residual structure, particularly using those Hodge GVFs, allows the model to capture much more complex patterns on manifolds than shallow approaches, like we saw with the wind data. This looks really promising for areas like climate modeling. Thanks for tuning in to the AI Research Roundup.